Hey y'all, I'm Sunny Shell, and tonight we're going to discuss the James Webb Telescope. So sit back, buckle up, and let's get to the sunny spot on Skeptic Haven.
Fabulous. I like that a lot. Like crop circles in secret are actually luminous at night. Here we discover them as the nebula part, and we present the name of our guest. And here we are, live.
Yeah, you definitely should have narrated that.
Yeah, sorry. Next time I'll be prepared.
Hey everybody, I'm so glad that you were able to join us. And anyone who has ever watched any of our shows, any of the Sunny Spot, knows that I geek out whenever I have our guest on. I would like to welcome Ethan Siegel. Hello, Ethan.
Hey, it's my pleasure to be here. Oh, this green screen is fun.
So for those who, for some reason, don't know you or haven't watched you on my show before, will you please tell everybody a little bit about yourself?
Sure. My name's Ethan Siegel. I'm a PhD astrophysicist since 2006. Since 2008, I have been writing the popular science blog Starts With a Bang. And I am just so excited to be able to share the latest news about the universe with everyone who's curious. So thanks for being here, and let's have a ball diving into the latest, greatest discoveries from the universe.
All right, absolutely. So for the viewers, if you have questions for Ethan, please be sure to drop them in the chat and we will get them up and ask them of Ethan. And if you are one of our patrons, you could even get our link and come on and ask Ethan on our show. So think about that if you want to be a patron. All right, we're going to dive right in. The first most important question: what is the Webb telescope and how is it different than the Hubble?
Okay, a lot of you won't remember this, but the Hubble Space Telescope was our very first space-based observatory that was capable of seeing the universe in a way that was better from the ground. And everyone should know, before we even got to James Webb, we learned more in the past 30 years of having space-based astronomy about the universe than we did in the 30,000 years prior. So the last 30 years have been revolutionary. Now, Hubble is great. You've seen pictures of it. It's this big telescope tube covered in reflective, what looks like aluminum foil. It's fancier than that, but only by a little. And Hubble is in low Earth orbit. Now, the thing is, from its location in space around Earth, 50% of the time, anything Hubble would try and look at is blocked by planet Earth. So that's one drawback. Another drawback is Hubble is always in range of planet Earth, which means the Earth heats it, any radiation emitted by Earth shines on it, and it's always in direct sunlight. Even with a reflective coating, Hubble really doesn't get like 100 degrees below zero. It gets close to the ambient temperature around it. That means Hubble can see ultraviolet light and it can see visible light, but as soon as you start to look at infrared light, you start having to contend with the heat of the telescope and the instruments itself. And third, Hubble is only a 2.4 diameter meter mirror. So in space, in astronomy, the things that determine how well you can see the universe is what's your range of wavelengths that you're sensitive to. Hubble has ultraviolet, visible, and a little bit of infrared. And what is the resolution of your telescope? That's the number of wavelengths of light that can fit across your mirror. So that's how good Hubble is. James Webb is a much larger segmented mirror. James Webb is about 7 times the light gathering power, that's surface area, and more than double the resolution of Hubble, which means you can fit more than twice as many wavelengths across it, and the images are more than double the sharpness of Hubble. James Webb is also optimized to be way the hell away from planet Earth. Pardon my French. It is 1.5 million kilometers away from planet Earth. It's about 4 times as far as the moon is. And it always has Earth on the away from the telescope side. So the Earth is over here and the sun's another 93 million miles that away. So what Webb does is it never has to contend with Earth being in the way. And the other thing it has is it has that miraculous 5-layer sun shield that passively cools the whole observatory down to about 40 Kelvin, and one instrument that's actively cooled through a brand new onboard coolant system down to about 6 Kelvin. So whereas Hubble can do ultraviolet, visible light, and a little bit of infrared light, James Webb is primarily designed to be infrared. It can do a little bit of visible light, but it can see to infrared wavelengths that are a factor of about 15 times longer than the longest wavelengths Hubble can see. So a lot of the things we're seeing in James Webb, yeah, they're brighter, they're higher resolution. It's going to reveal features that Hubble can't resolve, and it's going to better resolve features than Hubble could when they look at the same object. But James Webb Space Telescope is also seeing the universe in a set of wavelengths of light that no observatory has ever seen anywhere near this precision before. It's important to remember that James Webb and Hubble have a little bit of overlap, but what we really, really want, now that we've seen the amazing first images from the James Webb Space Telescope, is we want a new fleet of observatories that can observe the universe with as big a leap as there was from Hubble to James Webb in all the other wavelengths of light that there are to observe too.
That's so cool. Okay, so thinking about what you just said, my next question may, well, how do infrared cameras work?
So infrared cameras, they work the same way as a visible light camera, except most of the things that we see in visible light, like each other, we're seeing reflected light. We're seeing light that's, oh, we have a light source and the light is reflecting off of me and coming to you. That's not true in space. In space, almost all of the stuff we see, if you take out the planets in the solar system and their moons, it's almost everything we see. Stars, galaxies, these are things that generate their own light. So when you look at an image of the universe in visible light, you're seeing, okay, here's how much red light it emitted, here's how much green light it emitted, here's how much blue light we emitted, and we're stitching them together and making a color composite image. I don't like this green screen, so I'm going to turn this crap off. I hope you don't mind. It's bugging me.
That's okay. That's all right.
All right. So then you say infrared cameras, it's the same thing, except things that come up to a much lower temperature can be seen in infrared. When we're looking in infrared, we can see things that emit what we would perceive as heat and cooler things than what we would perceive as heat. And we can even see the radiation from things that if we touch them, we would be like, oh my God, I hurt myself. I gave myself a cold burn because they're so cold. James Webb Space Telescope can see things that are radiating down to about 10 to 25 Kelvin, just a few degrees above absolute zero. So whereas Hubble and most optical observatories are sensitive to stars and starlight, observatories that are in the infrared can be sensitive to specific molecules, to gas, to dust, to matter that's only now collapsing that will later form stars, and to things that are in the vicinities of stellar environments. So we can reveal properties and details about the universe that would be invisible to not only our eyes, but even Hubble's eyes.
Okay, well, that makes sense. So aside from the infrared cameras, are there other instruments being used? And if so, what kind of instruments? does
Well,
Webb
there
have?
are two infrared cameras aboard Hubble. There's the near infrared camera, which goes from, so I'm going to get a little technical and talk to
Okay.
you about wavelengths of light. And I'm going to talk about everything in nanometers, which will get me, a bunch of grief from practicing astronomers. But we're used to nanometers because that's what we see. Blue light goes at about 400 nanometers down to red light at about 700 nanometers. That's the full range of human vision, from that bluest, violetest 400 nanometers to the reddest, faintest, and all the spectrum in between at 700 nanometers. That's how much visible light can see. Now, NIRCam aboard James Webb Space Telescope starts in the visible light. It starts about 500, 600 nanometers, but it goes all the way out to 5,000 nanometers. That near infrared camera alone goes about a factor of 3 deeper than Hubble's most sensitive filter. But then on top of that, we have that ultra cold camera, the mid infrared instrument. And that goes all the way from about 5,000 nanometers to about 28,000 nanometers. We are seeing that particular wavelength of light to a much greater resolution than we've ever seen it. The only comparable space observatory we've had to view that wavelength was NASA's Spitzer Space Telescope, and Spitzer had about less than 2% of the light gathering power as James Webb has. So what it would take Spitzer a year to see at low resolution, James Webb can see the same thing in higher resolution in less than a week.
Okay, so what are we
Oh, I'm sorry.
hoping?
You asked about what else does it have?
Oh,
Yeah.
yes.
Why would we be caring about these two revolutionary things when surely there are more? Yeah, there are more. So what James Webb can also do in both the near infrared and the mid infrared is it has spectrographs, which means it can take the light from any object or a series of objects and break that light up into its component wavelengths. So you can say, oh, is there water inside this? One of the first science things James Webb did is it took a look at an exoplanet that passed in front of its parent star relative to our line of sight. And when that exoplanet passed in front of it, James Webb took a spectrum of it, which means all the light that filtered through the atmosphere of the planet, all that starlight that filtered through and came through to us, we could break that light up and see what was in there. And we found water. We found signatures of water that were super strong. And yet, even with that water, we found, guess what? Even with all the water vapor there are no clouds. This exoplanet atmosphere has no clouds, but a ton of water vapor. Fascinating, right? Then what we say is, well, what else you got, Webb? And it says, hang on, this spectrograph that I can use this to measure distant galaxies. So now when I get a light from a distant galaxy and I want to know how far away is it, I don't have to say, oh, I'm going to take the filters I have and make a guess. No. James Webb Space Telescope, what you can do is you can break that light up into all its individual wavelengths, and you can say, oh, there's a line here and a line here. And when I see that patterns of lines, I know this is the element oxygen. And the fact that I see them at these wavelengths and I know the atomic physics that governs an oxygen atom means I can know exactly how far away it is. This is something, if you went and looked at what is the farthest galaxy we've ever seen in the universe, for the past 10 years, we haven't had that kind of spectroscopic confirmation. They've all been guesses. They've all been unconfirmed. With James Webb Space Telescope, we're going to go back to confirming them. All these candidate galaxies you've been hearing about, no, you wait for that confirmation. Be responsible, because it's coming. And in science, we never substitute conjecture for the actual data.
This is really exciting to me because what I am hearing, and tell me if I'm wrong, this means if we can see the galaxies furthest away, that basically means we're looking into history and we're seeing some of the first, or the oldest, I should say, the oldest galaxies that are still around. Is that correct?
Yeah, imagine you were studying human beings, right? And you had the power to take pictures of humans from old age to, middle age to adulthood to young adulthood to adolescence, and the youngest child you ever saw was about 5 years old. And you would be like, "Oh, I understand how humans work," right? But then you'd say, "Hey, how come I've never seen a picture of a child younger than 5? Do they not exist? Do only 5-year-olds spring into existence and evolve after that?" No, you know that this child or this adult was at one point a baby, and then an infant, and then a toddler, and then a young child who grew up the rest of the way. That's the situation with Hubble. That's the situation before the James Webb Space Telescope. The big question with James Webb Space Telescope is, how far back will it be able to take us? How far back will we see things that we recognize as stars and galaxies? Will we see the equivalent of a 3-year-old? Will we see the equivalent of a 1-day-old? Where in between are as far back as we can see? As we go from newborn to infant to toddler to human, well, galaxies have their own life cycle. And right now we have theories, we have ideas, but we're missing the data. And there's no substitute for that. James Webb is going to fill in those gaps as far back as we can go. I wouldn't be surprised if it started finding the earliest stars and galaxies less than 200 million years after the Big Bang. You have to remember, the current confirmed record holder from Hubble doesn't send its light to us till more than 400 million years after the Big Bang. So James Webb is going to take us farther back than we've ever been. And there are some candidate galaxies, not confirmed, but candidate galaxies that may have already shattered Hubble's record.
Wow. Oh my, so we are really, basically, we are able to learn. Well, it's mind blowing. I can't even ask my question because my brain is just not even comprehending all of the different things. Okay, so let me back up here. What are some of the main science goals of Webb before we get too like totally geeked out?
This is going to show you my biases, because one of the things Ethan cares about that you're going to discover with James Webb. So some of them are obvious, right? We can see the universe that is sharper, farther back, fainter, and more pristine than ever before. But this doesn't just have applications to the first stars and galaxies. Obviously, we're going to see stars and galaxies farther back than we've ever seen them before. That's a slam dunk. But we're also going to be able to say, hey, look at all these galaxies we've seen before with Hubble. Are they rich in gas? Are they poor in gas? How does the gas within? The gas is the material you need to form stars. How does that evolve over cosmic time? What is the difference between a galaxy and a quasar? And how does one turn into the other? When do the first dust-free galaxies appear? When do the quasars stop quasing with their active galactic nucleus and become the galaxies we recognize? How long do we have to wait until the universe makes disk galaxies instead of irregularly shaped ones? What are the rotation curves of these galaxies like? And does dark matter evolve in galaxies, or does it remain constant? One of the surprises we've gotten from James Webb already is a lot of the galaxies that Hubble sees. When James Webb looks at those same galaxies, they found that Hubble's light was actually smeared out a little bit. And a lot of these galaxies that we thought were a certain physical size in space are actually smaller when we view them with James Webb, because James Webb gives us those sharper images. James Webb has that higher resolution, and it can resolve features. Whereas in Hubble, it might have just been a smear or a blob. In James Webb, we could see, oh, that's a disk galaxy, and it has this arm structure to it. So we're seeing the whole universe better than we've ever seen it before. But some of the biggest things that people are excited about with James Webb have nothing to do with stars or galaxies. They're doing things on much smaller, more local scales. How do planets form around newly forming stars? James Webb is answering that. What molecules are present in these protoplanetary disks and are available to help create life? James Webb is capable of answering that. When you take a look at these exoplanets that happen to be properly aligned with their parent stars for that light to filter through their atmospheres and come to our eyes, what are we going to find in there? Can we find signatures of organic molecules around planets that are only a little bit larger than Earth? Maybe. Let's look. James Webb is capable of making those measurements from solar system scales to stars, galaxies, and extragalactic cosmic scales, from the gas and dust to the star-forming material and the stars and the post-stellar death phase. James Webb, I would say, if I had to boil down what its scientific goal is, it's going to show us how the universe grew up. And that's a pretty remarkable thing to get to learn. You know, if you had come to me when I was a kid and said, oh yeah, how would you like to know these things, right? I would have said, these are questions that you ask philosophers or theologians or maybe poets, because this is way beyond the capabilities of science to answer. And I love that today, these are not questions beyond the capability of science to answer. These are questions that science is answering starting in 2022. And just like a good scientist, I can't wait to gather all this data and learn all the remarkable new facts and features about the universe that are out there. But I want us to not lose track of the importance of taking the next step too, because science is a thing that is in danger of ending every single moment that we choose to not invest in it.
Yeah, that's exactly right. And we need to vote for candidates, local all the way up, that trust in science, understand science, and will continue to fund science. That's just a little aside. So I'm curious, when did the James Webb Telescope launch?
Oh my God. So I'll fess up that I do not have a Christian background, but I got the best Christmas present of all. I woke up at like 4 a.m. on Christmas to watch the live stream of the launch of the James Webb Space Telescope. And for me, that was one of the most remarkable Christmases I've ever had. It's definitely the most recent Christmas I cried on watching this, because what happened was, the announcement was done in French. It was launched from French Guiana. And when that launch was going on, you could hear the French mission control, flight control announcer announcing that all systems were nominal, that everything was going during its journey into space. We knew that if everything worked right, what we would see was the James Webb Space Telescope. The last thing, once it made it to space, it would separate from the module. And it did. It separated from the module, and we saw it drifting into the sunlight, glittering on its trajectory. And then an unexpected thing happened. About 15 to 20 seconds after separation, the solar array started to come out. This was early. It was not supposed to come out for 3 to 5 minutes after that separation, and it started coming out in less than 1 minute. And that was when I started crying, because I knew that that meant that the launch was so pristine that it triggered the automatic system to say, don't wait for manual deployment. of the solar array. Automatically do it and start powering yourself now, because no other changes need to be made. The James Webb Space Telescope was designed to operate with certain parameters, and it was designed so that it would reach its destination and be fully commissioned and be ready for science operations that lasted between 5 and 10 years. Based on how successful that launch was, we can expect more like 20 years of science with the James Webb Space Telescope. And as a bonus, it is not operating at the sensitivity it was designed to. Its actual performance is about twice as good. This is really a testament to the people who designed it, who built it. This is a testament to how high quality the instrument teams are, that they understand their instruments so well that they can achieve this level of performance at them. And it's a huge, huge kudos to all the scientists, engineers, and technicians at NASA, the ESA, the Canadian Space Agency, and also at Northrop Grumman and all of their partners who built this and got it to the successful point where it's at. This is not something where like one person was a driving force who made this thing happen. This was a team effort of thousands of individuals all working together to push the frontiers of human knowledge forward. And wow, are they ever delivering.
So you said when it reaches its destination, has it reached its destination and it's just going to stay there, or
Yep.
So it's not going to go any further?
So this is the whole thing, right? Webb right now, JWST, is 1.5 million kilometers away from Earth, because as the Earth goes around the sun, right? Earth orbits the sun. At every point along this orbit, wherever you put the sun and the Earth, there are 5 points that exist in space that will keep the same relative position between the sun and the Earth. These are called Lagrange points, and they are the points where the combined gravitational effect of the sun and the Earth will mean that as the Earth orbits the sun, as the Earth goes around the sun, a spacecraft located at any one of those 5 points will maintain the exact same relative position between the Earth and the sun that it started off at. One of those points is between the Earth and the sun. That's the L1 Lagrange point. It's great for observing the sun and great for observing the illuminated face of the Earth. But it's a terrible place to put the James Webb Space Telescope. A third point is opposite the Earth, what the DC universe calls counter Earth, right? Where you would put something that orbited opposite Earth around the sun. That's real hard to get to. It's gravitationally unstable. It's not a very attractive point for missions. It's also impossible to communicate with Earth because you'd have to send your signal through the sun. 2 of the other points, L4 and L5, make an equilateral triangle with L3. And so they're way behind, way ahead. Around Jupiter, this is where all the Trojan asteroids are gathered, around these 2 points. But L2, the second Lagrange point, is the special one. That's where James Webb is. And if the sun is here and the Earth is here, L2 is on the opposite side of the Earth. So right here, on the opposite side of the Earth and the sun are always behind the James Webb Space Telescope. So the James Webb Space Telescope looks out this way at the universe, and its giant sun shield blocks all the light and heat from the sun and allows it to be passively cooled to these low temperatures. Now, the L2 Lagrange point is gravitationally unstable. So the 2 things that Webb needs its fuel for, why that launch was so spectacular, is because the 2 things it needs is, one is to maintain its stable orbit at L2, and the other is to point the telescope. That's it. As long as we have fuel in that telescope, we can do science with it. Even if it degrades, even if we run out of the onboard coolant because there's a leak, we can still do good science with James Webb as long as there's fuel. And with 20 plus years of lifetime ahead of us, I just couldn't be more excited for all the things we're going to have a chance to find, including right now, we're going to be able to observe objects with James Webb and Hubble at the same time, which is a remarkable thing to be able to do.
That's awesome. So with that, is there a way for, if anything was to happen, or something was to malfunction or anything like that, that we could get, I don't know, something else up there to fix it, to like work on it, to, to keep it running?
This is why so much testing was necessary. A lot of people were like, they should just launch it and see what they get. Stop waiting with all these testing and confirmation and all of that. No, we get one chance. Okay. We have never serviced a spacecraft that is this far away. We do not have existing technology to do it. We could develop it. We could develop a crewed or robotic servicing mission, but that technology does not exist today. So if something went wrong with JWST, as you famously know, there was a problem with Hubble's original mirror optics that had to be corrected. JWST could not afford to have that problem. It could not afford to. So it was really something that people were emphatic. We have one chance to get it right. We have one chance to get this right, and we better get it right. And did they ever get it right? So, I know that being careful, over-engineering things is not it's not something that fires people's imagination. Waiting, taking the time to do it right. This is not the sort of thing that people get excited about. But this is the payoff. Just like we got excited when we had our first Mars rovers that were lasting dozens of times longer than they were supposed to. This is the power that you see of what doing it right looks like. And
that's awesome.
I couldn't be happier about it.
So we have some questions from the audience, but before we go to that, I was hoping that our producer, Wes, could show some of the great pictures that we have that you shared with us. So if you could talk to us a little bit about this.
Okay, so this is the Southern Ring Nebula. It is a dying sun-like star in a binary system. On the left, you see the NIRCam image, which is the near-infrared camera. And on the right, you see the mid-infrared image picture. Now, if you look in the mid-infrared, what do you see? You actually see there's two objects there. One of them is the white dwarf that's dying, is the star that's blown off its outer layers, that's contracting down to a white dwarf. And the other one is the bright binary companion star that is still alive. Over on the left side, on the near infrared camera side, you see all these different colors, and those correspond to signatures of different elements in there. You have hydrogen in the outskirts, and you have richer elements like oxygen on the inside. You can see the wispy tendril-like structure where the gas is denser or less dense. You can see what looks like shells, which show you that this star has blown off its outer layers in chunks. And one of the things you can see in both images, some are seen more obscured in the NIRCam than in the MIRI image. You can see there are background galaxies. If you see what looks like an edge-on galaxy on the left side of the nebula, just above that, you can see where it pokes through the dust. In the near-infrared, you can't tell that that's a galaxy as opposed to a feature in the dust. But on the right side in the mid-infrared, you can absolutely see, oh, wow, that's a galaxy. Below and to the right of that galaxy, you can see there's another, what looks like a face-on spiral galaxy. That's almost entirely hidden by the nebula itself. one of the remarkable things that James Webb is showing us, it's so good at observing the universe, is even when we're trying to observe a dying star here in our own galaxy, it can't help but expose the universe beyond our own galaxy.
That's amazing. That's just beautiful. Now, tell us about this one.
So this is an image called the Cosmic Cliffs. About 7,000 light years away, there is this big star-forming region known as the Carina Nebula. And this is a small part of it. This was first imaged by Hubble a few years ago, but this is the near-infrared camera image of it from the James Webb Space Telescope. We can just see so many features, these knots of gas and dust, these young hot stars that are actually boiling and evaporating the gas away. Within these dusty regions, there are new stars that are actively forming right now inside of them. And that blue, it looks like evaporating stuff. Those are actually tendrils of gas that are reflecting the light from the hottest, bluest stars back at us. So this is a remarkable image that shows us the environments where stars are newly being born right now. Wow. This is the mid-infrared version of that same region of space. It's a section of it. But what you can see in here is there are actually, if you look to the left center of the image and you come right about a quarter of the way, it looks like there's some sort of bullet plowing through. Mm-hmm. And that is actually a shockwave being produced as possibly a young star speeds through that region. In the center of the image, you can see a newborn cluster of young stars that is shining brightly in multiple different wavelengths of light. And this mid-infrared image is showing us not only where these new stars are actively being born, it's also showing us where that gas is the densest, where the newest next generation of stars are going to come from. This was the very first image that was ever released. This was released a day before the others on July 11th. Even today, it's been, only 4 weeks since the first image was revealed. And this, for me, is like a feast for the eyes. This is a galaxy cluster, a distant cluster of galaxies that itself is located billions of light years away, about 3 or 4 billion light years away. And the cluster itself is called SMACS, or SMACS, I guess, if you want to pronounce it, 0723. But what we're seeing is not just the cluster itself, but all of the galaxies behind that cluster, where the cluster's gravity stretches, distorts, and magnifies the light from behind it. We are seeing objects here that are so distant. Some of them are coming from less than 1 billion years after the Big Bang. Some of the arcs that you see, like the one closest to the center on the left, that looks like you get an arc and then it fades out and then it fades back in. Those are multiple images of the same galaxy that are being stretched by the phenomenon of gravitational lensing. And it's worth noting that the Hubble Space Telescope observed this same region of the sky before, and the James Webb Space Telescope has already revealed objects in this field that were completely invisible to Hubble's eyes.
That's so cool. That's absolutely beautiful. And I like what Kathy Human has said. It's mind-blowing seeing all of those galaxies. It's just beautiful. So I do want to go.
Let it blow your mind. Take it all in and let it experience this. This is your universe, the same universe that gave rise to everything on our tiny planet. This is the story of how it came to be the way it is today. This is the story of what it actually looks like. And we're discovering it in a whole new way compared to how we've ever seen it before.
And I just can't even imagine anything being more exciting than this. It's just well, I'm going to take a few questions from the audience while I get myself to not geek out so bad. So we have one. This is from James Field. Any chance of seeing or IDing population 3 stars?
I suppose I have to tell your listeners what a population 3 star is. All
Yes.
right. So population 1 stars came about, we discovered the sun. It was the first star we ever knew. And we were like, okay, I bet you a lot of stars are like this one. So we're going to call this population 1. And guess what? Most of the stars around us are pretty similar to the sun, and they're also population 1 stars. But when we look out at a lot of the stars, we find that, a bunch of them are like our sun, which is to say, if you break the sunlight up into all its component wavelengths and say what's inside, you can say, oh, there's this much hydrogen and this much helium and this much oxygen and this much carbon and this much iron and all of these other elements. And what astronomers do is, because we're brilliant, we say, okay, everything in the universe falls into 3 categories. There's hydrogen, there's helium, and there's everything else combined. Everything else combined is what astronomers call a metal. Sorry to all of the chemists, all of the engineers, everyone who's not an astronomer out there. If you're not hydrogen or helium, to an astronomer, you're a metal. Carbon, metal. Nitrogen, metal. Oxygen, metal. Neon and noble gases, metal. Sorry, everything that's not hydrogen or helium is a metal. Population 1 stars have lots of metals. Like our sun has a lot of metals, right? Because it can do things like make rock and metal planets like Mercury and Venus and Earth and Mars. And that's what you can do if you have a lot of heavy elements. If you don't have a lot of heavy elements, like many stars do, particularly the older stars, we say you're a population 2 star. Population 2 was the second population of stars ever discovered. They tend to exist in the galactic halo, far away from the galactic center, and in globular clusters, which are found randomly around our galaxy. These are generally objects where there weren't very many generations of stars that formed before the current stars that we're seeing. So those are population 2 stars. But in theory, there should be a third population of stars, what we would call stars made out of pristine material left over from the Big Bang that has never formed stars before. That is one of the science goals. That's a reach goal for James Webb. Can it see these population 3 stars? Within the last 11 years, we've discovered our first population of pristine gas just a few billion years after the Big Bang. So it's possible that what James Webb will find is in the earliest objects it's seeing, in the most distant objects it's seeing, it might have multiple populations of stars. Because population 3 stars don't have any heavy elements in them, they are expected to form extremely massive stars that live extremely short periods of time. So it's very unlikely we're going to find population 3 stars by themselves. But it might be possible that we're going to find, boom, stars that form in a very young object where some of them are population 2 stars, but some of them really are population 3 stars that are forming from this pristine material left over from the Big Bang for the very first time. And that's something we'll have to wait and see. I wouldn't expect it right away, but I would keep looking, because if any observatory has what it takes to reveal it, it's James Webb.
That's very exciting. Another question from Atantlo. What means fully developed galaxies closest to the Big Bang?
So galaxies, they take a while to grow up, right? If you say I'm looking at humans and I can visually tell just from a visual inspection what's a child, what's an adolescent, and what's an adult. You won't be right all the time. You will misguess people's ages. But in astronomy, we have some ways of measuring it that we can say, okay, this looks like a grown-up galaxy. What does it take for a galaxy to be fully developed? Well, you'd want to say, like, okay, it has a regular shape with a galactic disk and well-formed features and a large population of stars and maybe a diverse population of stars. So you want to see a mature galaxy, not a galaxy that's still in the process of forming. Some of these galaxies may exist as early as maybe just a 500 million years after the Big Bang. It might be possible to have mature galaxies within the second 500 million years of the universe. Someone has put out a paper just last month suggesting maybe James Webb Space Telescope has already found one a little over 600 million years after the Big Bang. That would be the earliest evolved mature galaxy that we've ever seen. One of them even has somewhere on the order of maybe a quarter of the mass of the Milky Way at that early time. Now, we see a few galaxies in the late time universe that are hundreds, if not thousands of times as massive as the Milky Way. But when you see an adult in a classroom full of second graders, you kind of ask yourself, what's going on here? And that's kind of what we're seeing with James Webb Space Telescope. How do these galaxies get so grown up so fast? This is something that we can't maybe explain it right away, but that's part of why we do this science. I can tell you the exciting things that I expect James Webb to find, but very often when we look at the universe, what we find winds up surprising us and going way beyond what our imaginations could have expected, and that's part of why we do it.
Absolutely. And finally, from, I hope I pronounced this right, Monon, what do you think of this idea that 50% of the particles of the universe are bosons, Higgs, photons, etc., and the rest fermions, based on the supersymmetry, maybe?
It doesn't look. Now, I'll give you the caveat. We don't know what dark matter is, and we don't know what dark energy is. But the universe that isn't dark matter and dark energy, that's made out of the stuff we know, like normal matter, atoms, neutrinos, dust, gas, black holes, etc. It's about 99 point, maybe 99.4% fermions, and only a tiny bit bosons, mostly in the form of photons. Most of the universe that we know of is made out of protons, neutrons, electrons. A little bit is made out of neutrinos. The rest is made up of photons. But of that 5% of the universe, only about 1/100% is made out of photons. The rest, all fermionic particles.
Wow. Okay, so now I'd like to go back to some of those pictures, Wes. I'm sorry, my dog is barking and I can't control that. So we'll just get some of those. So if you could talk to us a little bit about this one.
Yeah! So this is a famous galaxy known as the Cartwheel Galaxy. And whereas most galaxies are spirals or ellipticals, or I would say the third most common shape is what we call an irregular galaxy, the Cartwheel Galaxy has a feature known as a ring, where it has this dense galactic nucleus and a giant ring of new stars around it. But what's remarkable about this near-infrared camera image from the James Webb Space Telescope is it shows you two features you wouldn't be able to see otherwise. One is all of this pink and blue strewn throughout the space in between the central galactic nucleus and the ring. All of this is the gas and dust that is dense, that has been heated through a shock collision, and that is in the process of actively forming stars. When you look to the left of this galaxy and you say, hey, what about those two other galaxies? You notice one of them looks like a boring spiral and the other one looks like it's on fire. The one that looks like it's on fire is the one that collided with the Cartwheel galaxy and punched through it and created this extended ring shape and all the material in between it. And we can tell because of the colors in this Webb image that show us, oh, wow, it's actively forming stars. It has collapsing hot gas. It is producing these ultraviolet photons. And so you can actually see, looking at this picture, oh, that's the galaxy that created this interesting shape that we call the cartwheel. And again, when you look in the background, look at all those things you see. Yeah, some of those points of light have spikes on them. Those are stars within our own galaxy. Everything else is a background galaxy that exists behind the main three galaxies of the cartwheel. And this is fascinating to me because we have a saying in astronomy that one astronomer's noise is another astronomer's data. For people who study the extragalactic background of the universe, for people who study what are the details of these deep field images, this wasn't designed to be a deep field image, but we're getting deep field quality out of these images for the background galaxies. There is so much more science that's going to come out of all of the James Webb data than even the people who proposed we should use James Webb to do this thing ever imagined.
Oh, this is just gorgeous. Tell us about this one.
Oh, wow. So this is a barred spiral galaxy. Our Milky Way is a barred spiral galaxy, but what you're seeing here that's so fascinating is this traced out gas where all of this pink stuff is. That is where new stars are actively forming. This is where hydrogen molecules, hydrogen atoms are getting ionized, having their electrons kicked off of their atomic nuclei from high energy radiation. What we're seeing is these are the locations where new stars are actively forming in these glowing red regions. And you can see around them where older stars and younger stars are in regions that aren't actively forming new ones right now. So all that pink you see are tracers of star formation and tracers of the gas that's going to collapse to form new stars in short order. So if you were wondering, hey, when I take a snapshot in visible light, I know I can see the stars, but where are the next generations of stars going to come from? That answer is right there in that pink color.
Oh, wow. Tell us about this. This is so cool.
This is a spiral galaxy that many of you have seen before. The galaxy is known as Messier 74. So if you Google Messier, Messier 74, what this is showing off is the warm gas within the galaxy. This is a never before seen view of what the spiral arms look like in this particular wavelength of light. And one of the things I love about this is you can see that gas-free central region. And another thing you can see is where there are holes or cavities blown in the gas, which normally arises from star clusters that have blown the gas away. So what you are seeing is a snapshot of a Milky Way-like galaxy, but you're seeing aspects of this galaxy that would never be revealed by an observatory that was less powerful or less wavelength sensitive than James Webb is.
Fascinating.
This is a quintet of galaxies. This is the first ever known group of galaxies that happen to all be in the same location in space. Only that's a little bit of a lie. These 5 galaxies, right? You can see on the left there's a galaxy, on the top there's a galaxy. Below that is 2 galaxies that are interacting, and below that is a 5th and final galaxy. The one on the left is not part of this group. It's hundreds of millions of light years closer than all the other members. It just happens to be serendipitously along the same line of sight. But what you're seeing are these long streams of gas that are being ripped out of the galaxy by the tidal interactions of one galaxy acting on another. What you see are streams of new star formation, of heated gas being stripped out of these galaxies, of new stars that are forming within these galaxies, and also, again, just an enormous number of background galaxies that are behind this, many of which have never been discovered. In fact, this is just the near-infrared camera image, and I don't think your producer has access to the mid-infrared image of this, but in the mid-infrared image, when that came back, it showed something spectacular that we did not know existed, and that was in that topmost galaxy. It actually looks like it has that patterned, spiky diffraction pattern in the middle of that topmost galaxy, because as we learned from James Webb, there is a supermassive black hole that's active in the center of that galaxy, and it is tens of millions of solar masses in mass, and and it lives there and it's active. And this is stuff that we've learned from just the very, very first science images to be released from the James Webb Space Telescope. It's been doing science for less than a month, and this is already how it's revolutionized how we view the universe. If you're excited about this, remember this fact, that 99.5% of all the data that James Webb Space Telescope will ever take is in our future. It's yet to be taken. So when you think about how awe-inspiring what we've learned from the James Webb Space Telescope already is, remember, it's less than half of 1% of what's out there to learn.
Wow. Oh my goodness. So when scientists are looking at what comes back from Webb, who decides who gets to actually mess with the data and like look at it and dissect it and send it out and do all of those things? Who gets to look at that stuff? Who gets to learn from it first?
Well, the people who get to learn from it first are the people who've been allotted telescope time on the James Webb Space Telescope. So before it was ever launched, you had 2 main types of observing categories. One is guaranteed time observations. These go to the people on the instrument teams. These go to the people who are most intimately familiar with the James Webb Space Telescope and its capabilities. And they, as part of their contributions to understanding the instruments, optimizing them, building and installing and all of that, they were given basically the opportunity to say, what are the most important things you can investigate? And they got to choose. So about, I think, 16% of the first year's science budget goes to those teams, and they get guaranteed time. And from what I've been able to tell, much of the most valuable science is going to come out of that, because these are the people who really know what will we do that pushes the limits of this telescope? What can we see better than we've ever seen before? And what are, those low-hanging fruits to just grab and say, let's give this to humanity? So that's a big part of it. The other 84% or so comes from general observers. So this is everyone in the astronomical community, they got to propose, I want to use the James Webb Space Telescope to do this. It was very competitive. They were more than able to fill out the first year's science budget, but that's who is going to get first crack at the data to do science with it. However, those are not the first people to see the images. There are people, like there are for all telescopes, there is a data pipeline. There are people actually operating the telescope, people working at mission control who make sure that James Webb is pointed accurately, that make sure that the right target is selected for the right amount of time with the right filters. They acquire the raw data. And it's very important. Anyone who works in astronomy can tell you, okay, the raw data is not what you want. The raw data is what you get, but in order to turn that into something useful, it has to be properly calibrated. And that is something that telescope operators and telescope experts are the people who do that. They have that requisite expertise. So there are people at Mission Control working on James Webb. They are generally the first to see the data. They do what's called data reduction or data processing. They basically clean up the images to make them science ready. And then they go over to the scientists for analysis. And the scientists can either take the images that they get, or they can say, you know what, I bet you I can do my own calibration better and, go nuts, because they have both sets of data. But they're not the very first to see it. The first to see it are the people making sure that James Webb Space Telescope is doing exactly what it's supposed to be doing.
This is so exciting. Okay, so we are out of time, unfortunately, because I could go on for a very long time. What I would like for you to do is give us your closing thoughts about the Webb telescope, and then also tell us how people can find you. What is there anything interesting or exciting that you're working on now? Just any of your closing thoughts like that.
All right. Well, look, we only get one universe, and yet it's so vast and so remarkable that whenever we have the opportunity to push the frontiers of it, of how far we can see, at how high an energy we can probe, at how low a temperature we can achieve, or in what wavelengths of light we can see to unprecedented sharpness, precision, and accuracy, we should do it. The return on investment economically is always a win for all of humanity, but the return on the amount of wonder we get, on the inspiration we get, on how we understand our place in the universe and how small and fragile our planet is, that's invaluable. That's irreplaceable. You cannot put a dollar value figure on that. And we get it at such a cheap cost where it actually costs society more not to build these observatories than it costs us to actually build them. And that's in addition to the wonder, the inspiration, the opportunities we create for current and next generation scientists. It's a no-brainer that it's worth it. So James Webb is the latest giant leap forward for humanity. Don't let it be our last. And then as far as if you like hearing from me about what's going on, my name is Ethan Siegel. I write the column Starts with a Bang. I've got a couple of books that have already been published. One is called Beyond the Galaxy. It's the story of what the universe is and how we came to know it, with no equations and lots of pictures. My other book is Treknology, the Science of Star Trek from Tricorders to Warp Drive. And I'm currently writing a new book that's called the Encyclopedia Cosmologica, where we're going to start before the Big Bang, and every time you turn the page, you come forward 100 million years, and you get the cosmic story all the way up until the present day. And if you want to pre-order that, I will drop a link in the chat so that you can put it in the show notes.
Oh, thank you, because I want that. I really do. And I had forgotten that you had done published the book on Star Trek, because I'm a huge Trekkie. And so I am now going to go and get that one too, because that is going to absolutely blow my mind. Yes, I've got to have that.
By the way, if you were wondering, we did get the license rights from Star Trek. So there are illustrations from a large number of the Star Trek series, all reflected in this book.
Oh my gosh. Okay, that is going to be my prized possession because that is so cool. Thank you so much for coming on, Ethan.
It was my pleasure. Thanks for giving me the opportunity to share a little bit about the joys and wonders of the universe with all of your listeners out there.
Absolutely. And I want to thank all the people who came on. We had such great conversations going on. We had Otangelo, we had Uncle Beck, Kathy Humanist, Aunt Kathy, just so many great people. And so I want to, we would do this for you. So we really appreciate all of our viewers. If you like what we do, remember to like, subscribe, share, hit the bell, all those good things. And if you would like to join our Patreon, you can get special perks like getting a link and you can come on and talk to Ethan just like I'm doing right now. So consider being a patron. Our current patrons are Kathy Cotton, Cindy Plaza, Bryce Aroni, Deborah Grace, Aaron Coalson, Phil Calderone, and myself. I want to thank the producers, Westfield and Kat, and the booking team, Aaron and Shane. Remember to check out our other shows, Secular Soapbox, Women Atheist Unloaded, and the Bible Says What? And I get to announce, and I'm so excited, our newest edition, Global Atheist. It premieres this Saturday at 2 p.m. Eastern Standard Time. And to spotlight our new show, we will not air Women Atheist Unloaded this Saturday, but we'll return next Saturday on August 20th. So be sure and check that out. In the meantime, for everybody, always remember to think critically. Good night, everybody.